everywhere, and LLM is also everywhere. And of course, recently, our Nobel wins in chemistry and in physics is also AI based. So there is a lot of discussion about AI. And we have a very important study that's going to be presented by our guest speaker. So, yeah, I would like to introduce the topic. So, there is always this question about do large language models perform the way people expect? One thing that makes large language models so powerful is the diversity of tasks to which they can be applied. The same machine learning model that can help a graduate student draft an email could also aid a clinician in diagnosing cancer. So I have a friend, Dr. Durya Onunatsu, is a medical doctor and a researcher, and he had created very different ways of trying to use only LLM in his actual research. So um, we see that it's very versatile. However, the wide applicability of these models also makes them challenging to evaluate in a systematic way. It would be impossible to create a benchmark data set to test a model on every type of question it can be asked. So, this paper, authored by our guest speaker, took a different approach. They argue that because humans decide when to deploy large language models, evaluating a model requires an understanding of how people form beliefs about its capabilities. Building off on this idea, they created a framework to evaluate an LLM based on its alignment with human beliefs about how it will perform a certain task. So, I would like to introduce our guest speaker. I forgot to also ask Darcel to play his music here. Maybe you can play it just before we are going to open the floor for questions. So, our guest speaker here, Dr. Keyon Vafa, is a postdoctoral fellow at the Harvard Data Science Initiative. His research focuses on developing ML methods to address economic questions along with using insights from the behavioral sciences to improve machine learning methods. Keyon completed his PhD in computer science from Columbia University, where he was an NSF GRFP Fellow and the recipient of the Morton B. Friedman Memorial Prize for Excellence in Engineering. And so I bring to you here our guest speaker, Dr. Keyon Vafa. Keyon, welcome to Quantum Photonics.
Thank you so much for the introduction, and thank you for having me. It's awesome to be here. It's awesome that you have this group and that you've invited me to come speak, and I'm honored to come speak this week, as you mentioned. Especially this week because of all the exciting news about AI and the sciences that we've been seeing with the Nobel Prize announcements. So with that said, I have about, maybe 25 minutes to a half hour of slides, and I will be referring to the slide number as I speak. If you have any questions during the talk, feel free. I don't know if we interrupt or if we, post comments, but I'll try to take the comments as much as I can. So this is work with a couple of collaborators, Shesh Rambachan and Senil Molinathan, who are both professors at MIT. So I'll go now to the first slide, like the first non-title slide. This is slide number 2. And I want to start by saying that as you probably know, we have a lot of large language models out there in the world. There are probably too many to count. But there's a bit of a conundrum with large language models, or LLMs. And this conundrum has motivated a lot of my recent research. So I want to start with the obvious, which is that large language models do something fantastic on a bunch of benchmarks. So if you look at metrics such as how well large language models do on AP exams, or how well they can perform, coding competitions or write essays as scored by graders, they are quite high. And they're not only quite high, but the rate of improvement in recent years has also been staggering. So these LLMs are measuring fantastic on a bunch of metrics in a bunch of categories. And now going to slide 3, it's not just the metrics that have truly impressed people. I think each one of us on this call has probably had an experience where we've played with a large language model and it does something truly amazing. So here's one in the slide is one of my favorite examples. It's from the Sparks of AGI paper, and it shows that if we ask GPT-4 to write a proof about there being infinitely many primes with every line that rhymes, it does quite a good job at writing such a paper or such a poem. Every line rhymes, and it seems to be a pretty valid proof. Now, I think we can be cynical about many aspects of large language models, and cherry picked examples, and maybe we ought to be, but we also have to acknowledge that their progress and their performance is remarkable. In 2017, I truly think no one thought this would be possible in as soon as 2022 or 2023. So at the same time, and now here I'm going to slide 4, there's a problem, which is these same models that can astound us on metrics and have truly amazing examples also do things that are remarkably goofy. So here's a fun example I like, where if you ask ChatGPT, if you give ChatGPT 3 possible travel itineraries, one with train, one with car, one with metro, and you give ChatGPT the number of the travel time and the travel costs, and ask which mode of transportation you should choose, ChatGPT does something funny. It says that to make a decision, we need to calculate the cost per minute of each mode of transportation. And it says, well, the train costs the least per minute. So you're getting the best deal on the train. So you should take the 400-minute train, which costs $29, as opposed to the 92-minute metro, which costs $32, because you're getting better bang for your buck. And even if there was an even longer train, if there was an 800-minute train, then that'd be an even better deal, because it'd be even better um, cost per minute. So this is one example of GPT-4 doing things that are true as something that is truly goofy, and I'm sure that each one of you in this room also has examples where you've seen LLMs behave like this. So now going on to slide 5, um, this is sort of what I think about as the conundrum, and here's the problem, which is how can we think about models that do both amazing things and truly goofy things? And how can I trust metrics that we have, like performance on AP exams and coding competitions? The metrics are clearly not capturing something that we're getting when we're playing with large language models. So how can we truly evaluate what they're good at and bad at? And so I want to point out that although I'm describing these problems with large language models, we've actually been here before. We've had a problem where there's been a combination of metrics where a model looks good if you look at its performance on benchmarks, where there was a wow, and where there was a goofy example. And so specifically, I mean supervised learning. And by supervised learning, I just mean the set of models that make single predictions, such as binary classification. Like, given pictures of dogs and cats, is each picture a dog or a cat? It's a prediction, 0 for dog, 1 for cat. So going on to slide 6, in supervised learning, we've had impressive metrics. We've seen benchmarks such as ImageNet, which is a very large object classification data set for models that take pictures and try to identify the objects, like dogs or cats. We saw amazing, superhuman performance on these data sets, and again with amazing rates of progress over time. In fact, performance on ImageNet is sort of what prompted the deep learning revolution in 2012, when we had a model that had much better a deep learning model that had much better performance on ImageNet than we did on than other models had on ImageNet. And so again, going to slide 7 now, we've also had these incredibly impressive examples that are being captured by the metrics. So here, this example is another example I really like, where where machine learning models can tell you, if you give them 2 pictures of a pig, it can tell you whether the 2 pictures are the same pig or not. And apparently this, I don't fully understand how, but these sort of these classification models about same pig or different pig have had quite a bit of uses, apparently for agriculture or farming. So now going on to slide 8, we've also had truly goofy examples. So what the slide is showing is that if you give a model an image classification model that takes an image and tries to predict what is in the image, if you give it a typical picture of a pig, it will do well and it'll say this image is a pig. But if you add a tiny bit of white noise to the pixels, so we can just sort of imagine this as kind of static, if we add a tiny bit of carefully chosen white noise and ask the model to make a prediction on this new image, which is the original image plus a tiny bit of white noise, I think we can all see that the model is a pig. The picture is a pig. It truly looks like a pig. It looks like the original pig. But the model thinks it's an airliner, which doesn't make any sense. I mean, maybe you could say the ears kind of look like an airliner, but I would say that the ears also probably look like an airliner in the first picture. So again, going on to slide 9, we have a conundrum here, which is we've had really impressive metrics and we've had truly amazing examples, but we've seen that the same model that can tell whether two pigs are the same pig or different pigs, it thinks that carefully chosen white noise added to images of pigs is an airliner. So, we've seen this all before, but you may ask, like, great, like, are we done? We learn how to fix these problems or solve these problems for supervised learning and, binary classification. So, does that mean we can figure out how to solve these problems for large language models? Well, to see that, let's look at how we actually did fix this in supervised learning. And so here, let's go to slide 10. So we can think about supervised learning as learning models that take inputs and transform them into outputs. So, for example, in the last slide, each input could be a picture. I'm calling that X. The output could be the image, a label of the object in the picture. So, pig or not pig. And F is a model. It's a neural network that takes the input, it takes the image, and it says, is there a pig in this image, or is there not a pig in this image? So we solve this problem in supervised learning by asking to evaluate models in supervised learning, we need to ask, where will these models be used? And the good news in supervised learning is that we typically knew how a supervised learning model will be used. And so we could evaluate it there. So, for example, if we built a model to tell us whether two pigs were the same or not the same, we would use it when you would use it on maybe camera recordings of pictures of pigs in farms. So we understood a distribution of instances that we needed to use to evaluate a model. And so we could say, okay, because this model is just going to be used to say whether two pigs are the same or not the same, and the kinds of pictures it sees are the kinds of pictures that are available on CCTV footage from farms, we can just evaluate the model by giving it other CCTV footage of animals on farms and seeing how it does on those images. So because we knew how models would be used and the kinds of things they'd be used for, we were able to form proper evaluation metrics. And all the deviations, all the sort of weird behavior, like the weird behavior I described in the last slide, where a model thinks a pig is an airliner, this happens when we deviate from the kinds of instances that the model is evaluated on. So the carefully chosen white noise, that's not a typical image of a pig from CCTV. That's some sort of adversarially chosen thing. And so the performance guarantees that we get are only for the kinds of examples that we evaluate on, which are pretty straightforward because we know the kinds of places a model will be used. So now we can ask the same question for large language models. Large language models are, again, functions that take inputs. Text here is the input, and produce outputs. Maybe the answer to certain questions are outputs. Um, so now the crucial question for evaluating a large language model is, where will a large language model be used? And if we know where it'll be used, we can evaluate it. So going on to slide 11, the the big challenge is that large language models don't have a single use case. They're general purpose. The same model can be used to write code in Java or HTML or Python. It can also be used to do clinical knowledge review, or it could be used to draw unicorns in Tixi, which is a plotting library meant to plot, graphs and figures in LaTeX. There's a nice phrase from this paper from last year that I like that says GPTs are general purpose technologies, or GPTs. So because these models can be used in any place in a lot of different applications, they vary from supervised learning, where we won't always be using the same model to tell if two pigs are the same. We might be using a model to both be a doctor or to write code or to draw unicorns. So now going on to slide 12, just recapping what I said, we need to, if we ask ourselves, where will LLMs be used? we the only way we can evaluate LLMs is by answering the question, where will LLMs be used? And so this is the sort of question that I've been fixated on in my lab and in my recent research, is how to resolve this conundrum. What constitutes meaningful evaluation of a large language model? And today I'm going to discuss one way that we can evaluate. And this way of evaluating begins by asking the question, how and where are people choosing to use large language models? So by modeling how people are using large language models, we can come up with better ways to assess their performance. And this isn't just an idea, it's a necessity, because as we saw before, the only way we can get guarantees to how models will perform is we need to model where and how they will be used. So in this talk, I'm going to build a model of, I'm going to talk about a model that we developed for how people choose where to use LLMs. And so if we go to slide 13, here's essentially the whole paper, the whole framework in one image, which is, where do people decide to use LLMs? Well, if you're like me, you'll sit down with a large language models, play around with it for a while, and decide what it's good at and bad at. Maybe I think it's good at English and bad at math. And so if I decide that, maybe I'll use GPT-4 to write emails and to help me with essays, but I won't use it to help me solve equations. So I'm interacting with the LLM in the first step, and then I'm delegating it. I'm deciding what it's good at and what it's bad at, and I'm deploying it to the things that I believe it's capable of doing. And I just want to compare this one more time in slide 14 to the classical way we evaluate in supervised learning, where, since supervised learning models are just developed for a single task, we usually have a benchmark for that task, like, is this a picture of a pig or not? Or is this movie review positive or negative? And so we can decide to deploy models based on how they do on specific benchmarks on that task. And I want to say that, there's nothing about this framework that excludes large language models. If we had like a stable list of tasks and had benchmarks for each task, we could also run models on benchmarks and see how they did. But in practice, there are so many possible LLM tasks that we can't possibly create benchmarks for each one of them. Like, which benchmark would tell you the best large language model for writing emails, or for suggesting good ideas for mathematical proofs. So because of that, and this is slide 15, our framework considers humans who form beliefs about what LLMs are good at, and then decide to use them for the things they think that they're good at. And so forming the act of forming beliefs about LLMs is an act of generalization. And I want to say that this is not something new to LLMs. We all generalize all the time. Like, when we talk to people, we make generalizations about what they're good at and what they're bad at. So if I talk to someone and I ask them a question about quantum mechanics, and they answer the question about quantum mechanics correctly, I'll make a few assumptions. I'll say, this person really knows their material about quantum mechanics. They are also probably quite good at math. They're definitely good at physics and probably quite good at math as well. But if I want recommendations to a Korean restaurant in New York City, I have no idea if this person's going to be good or not for that. So, I'm inferring some beliefs about what this person is good at, but I'm not inferring other beliefs. And so we do the same thing with large language models. We see that if a large language model is good at a very difficult math problem, maybe we'll think this model is LLM is also good at maybe an easier math problem. Maybe we'll also think it's good at some physics problem. But we probably won't make inferences about how good it is at completely unrelated tasks to math. And so this active generalization determines how we use LLMs. So I'll use LLMs based on what I think it's good at from the comparatively small example of questions I ask, which is comparatively small, to all the possible things I could use the LLM for. And so here on slide 16, there's a little bit of formality about how we model this. And we call this function, we call this active generalization as arising from a human generalization function. And this is just a way that to assign beliefs about how a model will perform on one problem after seeing how it performed on another problem. So there's this function, it takes two inputs. It takes for example, we can ask, what is a human's belief that a large language model that knew the quadratic formula can also tell us which number is larger between 9.11 and 9.9. So this is just sort of a general way of measuring, of formalizing the notion that people form beliefs about capabilities based on based on a large language model's behavior. And I want to say that throughout this talk, I'm going to assume that we're making generalizations. Just to simplify, we're making generalizations based on one example. I see one example, and then I have to decide what else the large language model is good at. But in practice, of course, we can extend this to many more examples. You can see 10, 50, 1,000 examples, and sort of the same logic applies. It just requires a little bit of different implementation. So now on slide 17, LLM performance, if people are deciding, or if people are playing with LLMs and deciding where they're used, it depends on a new kind of alignment, which is how well can someone accurately predict where a large language model will fail and succeed after interacting with it. So in other words, after seeing a few questions, how good am I at predicting what the LLM can do and what the LLM can't do? And there's a general theoretical result, which is that that it's possible for one LLM to be statistically better than another LLM, but if it's misaligned with this human generalization function, it means that I can't figure out what it's good at and what it's bad at. That maybe it answers very difficult math questions correctly. I assume it can answer very easy math questions too correctly, and it just doesn't. And so I decide to use it to answer very easy math questions, and I get very bad performance when I use it. So this shows why alignment is crucial, because we only get the reward from LLMs in places that we choose to deploy them. We need to understand what it's good at and what it's bad at to get the rewards associated with good models. And so the goal of this paper was to collect data about how people make these generalizations, um, uh, and essentially to measure this human generalization function. So we do this by collecting we survey respondents on Prolific, which is a platform where people sign up to answer surveys and questionnaires for academic research. And so we survey these people and we sort of ask them what their belief changes are when they see LLMs answer one question correctly. We show people a question, we say an LLM answered this question correctly. How do you think it'll answer this new question now that you've seen that it answered this old question correctly? And so here I'm going to start by going over some examples of generalizations. So this is on slide 19. A lot of the examples of how people generalize, they follow things that intuitively make sense. I mean, like, none of this should be new to us. We all generalize, so this is sort of like a peek into our minds to understand, this is just sort of, it should be a reflection about how we generalize. So this example on slide 19 shows that after people see that a large language model responded to a question about amino acids incorrectly, they think that that model is less likely to respond to a related problem about glycogen incorrectly. Now, this makes sense. I saw it's bad at chemistry. I think it's going to be bad at one chemistry question. I think it'll be bad at another chemistry question. On slide 20, we show another artifact of this behavior, where not all questions are related. If I see a large language model answered a question about a TV sitcom correctly, I'm not going to update my beliefs at all on whether it answers a very basic arithmetic question correctly. It's just totally unrelated to knowledge about the sitcom. We also have asymmetric updates, and this is on slide 21. So after people see a very basic looking problem where there are objects on a nightstand and the first sentence says the booklet is orange, then second sentence says is the booklet orange, this is a quite an easy problem. So if people see that an LM answers this question correctly, we don't really update our beliefs about whether we think that that same model would answer a question about vitamins or enzymes, a much harder question about vitamins and enzymes correctly. However, if we see that the LLM flubbed this question about saying the booklet was orange right after seeing the booklet was orange, then we're going to say, okay, this thing isn't even capable of doing this basic recall. I probably think that it can't answer questions about chemistry, which are much harder correctly. So this is just sort of the structure of how people generalize, and there are all these. These are just a few examples. We have more in the data that we collect. These are no way representative of all the ways people generalize, but these are sort of a few ones that kind of made sense to us. And so now on slide 22, we ask how predictable is the human generalization function? So in other words, if I see an if given an example of a question and how an LLM answered, how well can we predict whether it causes people to change their beliefs about new sets of questions? And so we answer this question by fitting different models to model the human generalization function. And we find that the human generalization function is quite predictable, that we can predict with a reasonable level of accuracy how whether people will change their minds about whether an LM can answer a question or not based on how after seeing how it responded to another question. And so given this model of the human generalization function, we perform a simulated exercise, which is described in slide 23, where we simulate, if people see how a large language model answered one question. So here the sample question is, what's sine squared of x plus cosine squared of x? If people see that an LLM answered that question correctly, we use our model to form beliefs, that a person's belief that that same LLM will be correct on every other question. So maybe an LLM that answers this question correctly will maybe people think that it has an 85% chance of answering a new question about which is larger, 9.11 or 9.9 correctly. And so we simulate a setting where we say we're going to use an LLM to answer every question that is above some threshold, maybe like 80% probability correctness. And by doing this, we're simulating a scenario where people are choosing to deploy LLMs based on what they think the LLM is good at. And those beliefs are coming through human generalizations. And so the figure in slide 24 shows what we find. So this table, every row in this table is a different large language model. And I want to first look at the left-hand column of this table. And this left-hand column shows the accuracy at humans who are predicting whether an LLM will answer a new question correctly based on how it answered the previous question. And so we find that across the board, human accuracy is quite low. That all models are below 60. For all models, humans only have about a 60% accuracy. And the largest and generally accuracy scales with model size. That humans are best at predicting the performance of, or best at predicting how models will do when the models are larger. The best model is GPT-4. But as we move on to the right, here what we're doing is simulating the fact that in some cases, the different kinds of errors are asymmetric. So if I'm a hospital, for example, and I'm using an LLM to diagnose a disease or something, I care a lot if I deploy it and it gets it wrong. If I don't deploy it and it would have gotten it right, that's another kind of error, but it's a far less costly error than deploying it and having it get it right, than having it get it wrong. And so here that we show that when we simulate these settings where the cost of mistakes is increases, we see the trend flip. We see that statistically better large language models can perform worse when they're deployed by humans. And so the basic intuition here is that people form over optimistic abilities about what LLMs can do and can't do based on seeing how they responded to certain subsamples of questions. And so because the more capable models answer more questions correctly, people form more optimistic beliefs about what it can do and what it can't do. And so when we set the cost of being overconfident to be large, then the statistically better large language model will perform worse when deployed by humans. So in slide 25, we have examples of what generalization failures might look like. So all of these examples on the left are examples where if a human sees a large language model answer a question on the left correctly, they expect it to answer a question on the right correctly. However, large language models, specifically this is Llama 2 70 billion, they answer questions on the left correctly, but don't answer questions on the right correctly. And so, I'll just focus on the second example here. The question on the left is a question about, Alice and Bob and Claire are on the same team in a soccer match. Alice is fullback, and then she trades positions with Claire, yada, yada, yada. And it asks, what position is Claire playing? So the question, and Llama gets that right. That same Llama model is seen another question about Alice and Bob and Claire in a soccer match. They have slightly different positions, and it gets this one totally wrong. And so this is an example of a human misgeneralization. We think that an LLM that gets the question on the left right will get the question on the right right, but it doesn't behave like this. And going to slide 26, I want to point out that this isn't anything new. If anything, this is just this just generalizes behavior that we've seen before. Here's an example I really like, where on the left, and this is from a paper called The Reversal Curse, where if we ask GPT-4 who is Tom Cruise's mother, it answers correctly. It says Tom Cruise's mother is Mary Lee Pfeiffer. But if then you ask GPT-4, okay, who is Mary Lee Pfeiffer's son? It says, I have no idea who Mary Lee Pfeiffer is. I don't know who their son is. So the reason we find this so frustrating um, is that this is an example of misgeneralization. Any human we ask this question to knows who Tom Cruise's mother is also knows that Tom Cruise is Mary Lee Pfeiffer's son. But because LLMs don't obey this is an act of misalignment between humans and large language models. And so going on to slide 27, just closing out, the last couple slides, and this is a bonus slide where in this talk we've described large language models and whether or not they're aligned with the human generalization function. But we can also ask, are humans aligned with the human generalization function? When I see that a human answers a question correctly, how good am I at predicting how good they'll be at answering other questions? So we ran a very, small scale version of this experiment. This experiment is a little costlier to run than the previous one because we need to collect data about not only how humans generalize, but also what humans are good at and what questions they get correctly and incorrectly. So we did this for as quite a small sample, but we found that generally humans are good at generalizing other humans. That when we think a human will be incorrect based on seeing their performance on another question, they're probably incorrect. And when we see that they're accurate based on their performance on another question, they're generally accurate. And when we're uncertain, they'll get it right roughly 50% of the time. And this plot on slide 27 shows that large language models don't obey this. The lines are much flatter for large language models, and they don't seem to scale with accuracy, or sorry, with model size. So we generally don't see that we see that large language models are less aligned with the human generalization function than humans, and scale doesn't seem to help. So going on to slide 28, I just want to talk about limitations and what I think are some exciting next steps. One is that this paper has just used a single human generalization function across humans, but of course it varies across humans. So this paper is just about the aggregate function. I described how we're also just using single question examples, and it would be interesting to see how generalizations work for multiple examples. We just measured the human generalization function in 2024, but the generalization function is changing. I'm sure we all have different models about what LLMs can and can't do now than we did 2 years ago, and I'm sure that'll be different in 5 years and 10 years. So this is, these are sort of living artifacts. And so I want to close out on slide 29 and say that the generalization of large language models isn't just something that affects. It's not just an abstract concept that affects researchers and people who want to deploy large language models. It affects all of us. And so this is because a couple of weeks ago, OpenAI announced this new large language model O1, which had very good reasoning capabilities. And on the bottom left, it showed that this model performed very well at AME math competitions. 83% accuracy. It's insanely well. And so I thought, wow, this model can do amazing things. But then I was on Twitter later on and I saw this post from Yuntian Deng, and he showed that if you give O1 multi-digit, if you ask it to multiply two numbers, it starts to fail miserably once you move past 6 by 6 or 7 digit by 7 digit multiplication. So the same model that can get 83% accuracy on AME can't really do more than 7 or 8 digit multiplication. And so this is just an example of where I misgeneralized, where I thought that surely a model could do this, could do basic math, but I was incorrect. And so that's all. Thanks for coming. I just want to close by saying on slide 30 I have a link to our GitHub, which has our code and our survey data, if any of you are interested. So thank you for coming, and I'm excited to continue this conversation.
Thank you so much, Keyon. And I would like to announce to the audience that we are opening the floor for questions. And yeah, if you have clarifications to ask our speaker, please raise your hand. We will bring you up the stage. And also, to reset the room, for those who came in late, I would like to reintroduce our guest speaker. Keyon Vafa is a postdoctoral fellow at the Harvard Data Science Initiative. His research focuses on developing machine learning methods to address economic questions, along with using insights from the behavioral sciences to improve machine learning methods. Keyon completed his PhD in computer science from Columbia University, where he was an NSF GRFP Fellow and the recipient of the Morton B. Friedman Memorial Prize for Excellence in Engineering. So yeah, I would like to welcome Ayo or Eric also here on stage. He is with the Quantum Photonics team has been for a long time and is our regular moderator. So before I turn over the mic to Eric and also ask other people to come, I have a question which is a little bit unrelated to what Keyon has discussed, but I'm sure that he can answer this. So yeah, I saw Keyon. I saw in your bio that's online um, the papers that you made and also the previous experiences that you had, and it seems as if you are working basically, maybe quite instinctively on a multidisciplinary field. And yeah, I saw one of the studies or projects that you made even was about tiger moms. So yeah, how do you think because of the recent Nobel Prize win involving AI, there was a joke also about the next Nobel Prize in economics and also the Fields Medal. Can you make some comment about it?
Yeah, I think it's really interesting and exciting to see all the excitement about Nobel Prize, about AI, and seeing the Nobel Prizes this week. I'm curious to see what happens on Monday when we see economics. And I will say that I think the thing that drew me to AI was its applications, not just its applications as like an LLM, but its applications across fields. And so as you mentioned, some of my work has been interdisciplinary. During my PhD, I started focusing on how we could use model transformers, which are the models behind large language models, how we could use those to answer economic questions, and economic questions like what's the gender wage gap. So I spent a bit of time doing that research, which I found really exciting. But I would say, like, more recently, I've sort of flipped the arrow the other way, so to speak, where the in my PhD it was asking how can ML help the social sciences or the behavioral sciences. And now I would say that this talk that we've described today is flipping the arrow. It's asking how can the behavioral sciences help machine learning? And so I think this feedback loop is incredibly exciting, and I would say one of the most exciting things in the field right now.
Yeah, thank you so much. I myself I'm very much excited and I'm very multidisciplinary. In fact, of course, I had been a fan of complexity for a long time. And because I always post papers from physics, neuroscience, biotech, um, AI, and other fields, I could already see the big crossover and the usage of AI as a tool in order to further this study, which will help humanity and also fast forward, what we had studied 100 or 200 years ago. And remember, we also have this project by Sebastian Chong of Princeton about the brain, the mapping of the brain, which has recently been released. So I think this is very exciting. Anyway, I asked you because I could envision a lot of future rooms with you, and very interesting rooms because it's multidisciplinary and very relevant. So before I talk a lot more, I will ask you some questions later, but I'd like to give the floor to the audience first because, I think they are very excited to ask you questions. So we still have Eric here and Candace who came on stage. I'd like to give the mic to Eric now. Eric?
Oh, okay, okay. So I threw in a bunch of questions, kind of catching up because I came in late. My I guess my most pressing question is like, I guess human expectations expect that the models behave that same way. There's the famous image by Jan LeCun that talks about like the divergence of these systems. I'm just going to post it as my profile picture. Um, Let me see if I can shift this over a little bit. Let's see, the token of tree of correct answers and tree of all possible token sequences and how strange things happen, almost like nightmare scenarios. I describe it something like being analogous to Michael Fassbender's character in the movie Prometheus, that there seems to be something that happens in token prediction. The systems seem to be a little bit more convergent when they're put into agent frameworks. So I think of token prediction as being more like heat in an engine. And so you have to divert or direct the heat to do something useful with it. In this case, something like local memory. How could architectures basically mess with different people's expectations? Because I suspect that there is some sort of common set of tools that we're all using and we're building similar systems, but there are some systems that are distinctly different and perhaps in that way they're more alien than expected. Have you seen any such edge cases or anything like that? Thanks.
Yeah, yeah. So let me just make sure. I think I understood the question, but if I don't, please feel free to I'll obviously follow up. And so there's this question about like, first of all, like modeling language is just an incredibly difficult thing because we have this thing called the cursive dimensionality, which is that as sequences get longer and longer and longer, all the possible sequences, all the possible, there's just exponentially many possible sequences. Like once you get to like sentences of length, I don't know, 50 or something, it becomes larger than the number of possible atoms, the number of atoms in the universe. So every model needs to make assumptions on reducing that space. The human brain is one such model for reducing that space. We have some sort of underlying concept of semantic meaning. The transformer has its own one too. And the main thing we've described in this paper is asking, you know, how well do those things align when they have to go from small examples to large examples, or for they go from one example to another example? That's one very specific question. And so we found they don't align much. And I think that sort of goes with the experience that a lot of people have had with transformers, that in some ways maybe they align, but in other ways they don't. So then there's a question about whether sequence modeling alone will get us there. Will get us to like truly like understanding, or at least alignment in terms of our conceptual imagination. Personally, like I'm pessimistic of that goal, that really any model at predicting next tokens can get us there. I have another paper about trying to understand the world models that transformers build, and so in this paper, which I won't talk about too much, but we ask, if we train a language model on essentially GPS directions from Google Maps on New York, if we just say, if you start at Grand Central and go north, 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 east, 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 you're now at Penn Station, and we give it millions and millions of those, cannot learn the map of New York. And so we find that models can do really, really well at next token prediction. They can always predict what the next turn is. But then when we try to extract what it thinks New York looks like, it's just completely nonsensical. So maybe I can sort of I can go on and on and on about sort of like the world models of large language models. I'm generally, I would say, sort of I would say kind of like Yan in that sense, in terms of I agree with him that next token prediction, I don't see it as getting us there.
Okay, thanks. I'll leave it there for now, Cecile.
Yeah, thank you, Eric. So, Candice, thank you for coming up the stage. I'd like to give the mic to you now.
Hi everyone, how's it going?
Hi.
Keyon, hey, just a quick question before I ask my main question. Why are you so interested in the Bayes rule?
Yeah, I love Bayes rule. My introduction to machine learning was a probability class, and especially a Bayesian probability class. And so I my PhD early my PhD was focused on Bayesian machine learning, and there is some Bayes in this talk too, like how we update our beliefs is Bayes when we see new evidence. So Bayes rule is everywhere, and if everywhere you look, and if you look at Clubhouse, you'll see it on my profile.
All right. So my second question is, this is actually not my field. There's a field called neurosymbolic natural language processing. Are
Hmm.
you familiar with it? Do you,
Not incredibly, no.
yeah. Do you think the reason that the new O1 model is performing better is that they're probably using something like that, or do you think it's just like a deeper, like more layers model, this new one?
Yeah, it's
Why do you
hard to
think it's
say.
performing better? Yeah.
It's hard to say, and sort of because obviously OpenAI is kind of like tight-lipped about what they do. My guess is that it's not just more layers. It's not just scale. It seems like it's doing some kind of extra computation at like when we ask the questions. And so I don't know exactly what this computation looks like. Like a very basic form of computation would be chain of thought. Chain of thought is one way to prompt large language models, where you say, if you give a large language model a problem, if you just sort of add at the end, like, write out your thought process step by step, it's it is increasing the computation the transformer is doing, because it now, instead of just saying a single answer, it now has to say, oh, like, these are all the steps I took. But it's also making the answer better. People find that empirically, chain of thought improves how the large language model answers. So chain of thought is one very basic kind of, like, we call it like test time computation, or it's just extra computation does after you ask a question. And so I imagine that they found some interesting, like, new ways to do test time computations to beef up the model. That's just my guess, but who knows?
Uh, is it? Well, I always thought that it probably wouldn't get very good at reasoning, and my reason for this was that probably the model needs to learn how to break like sentences into propositions, like identify, like logical connectives, and then do a like natural deduction tree. And until it does not do that, it probably is going to fail in like new problems. Would you say that's accurate?
Yeah, I think that's right. I think, like, the model will succeed, like what you're talking about, like sort of like the tree, is the model will succeed at doing the tasks we think it can do if it has the same quote unquote world model that we have. If it sort of parses grammar the same way, and it knows basic rules, it knows that we have these laws of science, we have these laws of physics, etc. And so, like, while it's possible that the model can, hypothetically possible, the model can just infer these rules without, like, direct supervision, it seems unless that theory it holds, then it seems like nearly impossible for it to get perfect performance.
One last quick question. If you had to conjecture what the growth of large language models, like their strength, looks like as far as a graph, what graph would you conjecture it's going to look like in the long run?
I think we're going to have I don't know what large language models will look like in 5 years. I think we are,
I know, but as far as strength, like
as
is
far
it
as
going to go
strength.
exponentially up, or is it like going to converge into like
Yeah,
going to
it's a
get
great
stuck
question,
somewhere? Yeah.
because we're definitely in the exponential curve right now. Just in when you're in exponential curves, it's really hard to say, if we're near the end or if we're near the beginning. My guess, and maybe I'll, like, bite my tongue on this. I don't hold this too confidently. Is that we're near the end of the exponential curve, and I say that because I feel like the updates we've had since GPT-4, in the sort of year and a half since GPT-4, seem to be far less than the updates we had the year and a half before GPT-4. So it feels like it's slowing down, but at the same time, maybe progress is being made and it's just sort of being kept behind closed doors in industry. I don't know.
I actually found equivalent performance to O1 preview with when you put like GPT-4 into an agent API system. So you could run this kind of loop locally, and I found that to be just as competitive. So I don't see much performance difference in the last 2 years. But I think the interesting thing is that the system scaled from like 80 points of IQ to 120 points of IQ. And that's enough to offset a significant amount of work so that humans can focus on other things. I think when you think of what the system can generalize, I think there's economic kind of twists there that people might make, as you said, wrong assumptions about what the model can do. So it seems that the model has to be reminded of its own limitations. Any comments on that?
Yeah, that it's a good observation. That's hilarious that you found that O1 is as good as good as GPT-4. And it also that reminded me that like while I think that maybe like performance in some way has plateaued. One of I think the most exciting things is both the size and the openness of the new models that we have. Like I think Meta is doing incredible work in terms of releasing Llama, Llama 3 that essentially replicates the closed source GPT-4 on many benchmarks, making it open for everyone and making it something like 500 billion parameters, which is not small, like we can't all use it, but it's sort of it's at least all the parameters are available. And at the same time, they're releasing like 1 billion parameter models, which we can all use, we can all pull up on a Colab notebook. So I think the openness is one of the is the openness and the getting things small. Apparently also to work on my phone. Like who knows? Maybe I'll have a 1 billion parameter language model on my phone is incredibly exciting. I think you asked one more question, which I forgot.
Yeah, I find it pretty impressive the kind of things that Carpathia and others are doing with LLM.c and just getting these things down to like a single file, which is kind of nuts. Makes you think of like, hey, what am I worth?
Yeah,
Like
exactly.
carbon footprint of a human versus these systems. Kind of
Yeah,
puts us to shame.
absolutely. Yeah. Yeah, I love Carver these videos. I should just say, like his I when I was like in the last year of my undergrad is when he was like writing his blog posts about like recurrent neural nets, and my first exposure was like using his code to like write Shakespeare. And now I'm like I'm still following it. I'm still learning from him. Like his Nano GPT code base and tutorial on YouTube is one of the best things I've ever seen. He's incredible.
Yeah, thank you. And we'd like to give the mic now to Kevin. Kevin and Dr. Didi, welcome on stage. Kevin, mic to you now.
Oh, okay, yeah, yeah. But mainly, I have one question, one specific question, and then more of a general one. But rather than asking a million, basically, I heard that they're based off neural networks, LLMs and AI, and so they forget things, in the middle. They remember things better at the beginning and better at the end, like humans. And I'd like to see if that's true, and or if you can speak on.
So by beginning, middle, and end, are you sort of saying like when I talk to you and I tell you a story, you'll remember the beginning of the story, the end of the story, but not really the middle of the story correctly? Or well, is that what you're saying?
Yeah, yeah, exactly. That's what they use. And the more tokens you use, obviously, it gets more convoluted. But yeah, that's the gist of it. That's
Yeah, I can speak to that generally. Specifically, in this paper, we didn't really explore that hypothesis because we were just looking at sort of fixed length queries. What I have noticed is that there definitely is a steep drop off in terms of length. I haven't done exercises where I've looked at beginning, middle, and end, but I've done things where I like give an LLM like a prediction problem, like a very easy prediction problem, where like I the it like has to learn a pattern that's like very basic, and the pattern should be very obvious from like the first few numbers. And I noticed that when I add like 10 numbers or 100 numbers that are just random noise, like just like a bunch of zeros to the end of the question I ask, it does much worse when I train. And it's sort of like it's finding a needle in a haystack. Um, Humans we're like good at like differentiating some needles from some haystacks, if the haystack doesn't look like the needle. But to LLMs, like this all kind of looks like a haystack and a needle. So it gets very like easily distracted when you add more things.
So it seems like the secret recipe is like, hey, how do you train your AI, or like, what's the syllabus for your agent, so to speak, and seeing how people select different texts. Like the one interesting thing that I've heard is something from a character known as Adrian Dittman, and how he seemed to have so much knowledge about how AI systems are built by OpenAI, and he specifically commented about something like only a subset population of tweets. So there's like this population of about 100,000 people on Twitter whose entire Twitter feed is part of like the training data set, which is kind of interesting because that means that you're quite literally picking people that you like and you want your AI to be like. So it's kind of, it gave me a new appreciation for these kind of systems as being a city of ghosts.
Yeah, I mean the how you train the data you train on is super important. I mean, I personally I train like any of us. I follow kind of these tutorials. I don't have a secret sauce. What I've heard is that inside these companies that are developing large language models, they've found that the data curation is one of the most important things. That we can't literally just scrape everything off the internet. You really have to prioritize the high quality material. You have to pay people to produce high quality material, and you have to upweight sources like Wikipedia or whatnot. And you really have to be quick to discard junk, and that makes quite a big difference.
Yeah, but that's kind of like raising kids, and we know how to do that. So I don't know why everybody's panicking, but it is exciting that robots can think. Because I've actually found it to be quite useful experimentally and in generating questions. But I'm going to let the next speaker ask their question. Dr. Dino, you want to go ahead?
Yes, yes, thank you. Sorry, this is Alex Dinovitzer. Sorry, I changed my profile.
Dr.
Mm,
Dino, can you please come closer to the mic?
yes, is this better? Is this better?
A little more, please.
So, can you hear me now? I don't know what's.
I can hear.
Okay, good. Thank you. So my question is about what training set of data is being used to train these LLMs. Now, my understanding is that it's just the freely accessible data. However, historically, the largest repository of knowledge is actually not the internet. It's a database called LexisNexis
Mm-hmm.
that contains all the newspapers, articles, etc., magazines, etc. And even before the internet, before the web, it was the largest uh, database in the world, and right now I don't know how large it is. It's probably like orders of magnitude larger. Furthermore, it includes content that's almost exclusively written by professionals rather than, schmoes on Reddit. Now, my question is, this data is not currently a part of any training set in any of the models. Is this correct? And if if it is used to train LLMs, how will that improve the LLMs that already exist? Thank you.
Yeah, great question. So I want to start by saying that in the early days of large language models, like GPT-2, for example, that was trained using only publicly available data. Like that, I think was just trained using like I think literally articles that were linked on Reddit. But over the past few years, while there are some open source replications that only use publicly available data, the private companies, a lot of their success is moving beyond publicly available data and using private data. And so a lot of this is sourced directly from the companies. It's they ask people to create data. Sometimes they have licensing deals and they're getting like I think Reddit, yeah, just like as you maybe mentioned, signed the deal with I believe it was OpenAI. So and my understanding is that these high quality data sources do add a lot to the capabilities of models. So even like Llama 3, which is widely released, it's open source. The anyone can download it. it's still not entirely clear what exact data set they were using. They haven't released the data, and I don't know that much about the data set that they used. And so, with respect to that LexisNexis, I actually recall hearing something that I'm sure, and I remember reading that LexisNexis is itself looking to develop its own large language model, and I'm sure that like GPT-4 is probably very excited about the prospect. Or I'm sure OpenAI is trying to get some sort of deal with LexisNexis. I imagine just because it would be very valuable, and I imagine that it would be a big boon to OpenAI, because the sort of the not so secret is that we're running out of training data. Like at some point, we've used all of the internet that we can harvest, and if we need tons and tons of data for these models to do tons and better, that might be one reason that we've plateaued. And so I think these next couple of years it'll look interesting to see, like, will places follow the model set by like Reddit, and I think Financial Times did this as well, where they create licensing deals with companies, or will there be more issues like the New York Times, which has sued OpenAI because it didn't let them, because it never gave OpenAI permission to use its articles, yet it's found evidence that it was trained on its articles and can regurgitate some of them.
Yeah, I don't know if that's copyright law though, right? So that could be a whole other debate on its own.
Exactly, yeah. Yeah,
There's
I
a
have no
new,
idea who's going to win that.
yeah,
The
there's a new
people with the better lawyers, that's for sure.
Yeah.
there's a new paper which I haven't read in detail yet, but it's I think related to your study, or more information for your study in the future. It's about aligning LLMs with individual preferences via interaction, because this paper is from I think University of Illinois Urbana-Champaign and SoCal, and usually the research on LLM alignment largely focuses on training models to adhere to broad generalized human preferences. However, how individual users may interact with the models in diverse ways, expect different types of outcome from them, is often overlooked. So they started to build a diverse and detailed user personas pool that can guide long multi-turn conversations on an iterative self-generation and semantic similarity based filtration process. So this is their method in order, maybe one of the ways to make the LLMs align with human preferences. So I thought that, this is kind of related to the paper that you have. Any comments?
That sounds great. I'm actually not. I haven't read this paper, but I would love to read it. So if you can send me the link, I would love to take a look.
Yeah, I think it's really very interesting because suddenly, it came to my feed, and I was very reminded of how, researchers try to make an alignment. Sometimes they don't talk, but here in Clubhouse, we had experience because we had interviewed many people from different fields. For instance, Michael Levine from the field of bio, and also someone from Imperial College London who is a neuroscientist, and another one from Harvard, I think Jeremy Guanadera. And actually, they are researching on separate fields. However, the thoughts and the theories and the findings of the papers that they have uh, aligned. So we asked them to collaborate on this. So that's why it's, I think, very interesting, because for the sake of humanity, of course, I think this is very important. So I will give you a link to this by email. And anyway, I want to ask you also. I got a question from one of the audience. I was messaged by the audience. Her name is Anna. How do you see your research, this research in particular, intersecting with ongoing efforts in explainable AI? Could better interpretability of LLM decisions help bridge the gap between human generalization and LLM behavior?
Yeah, exactly. That's a fantastic point. That we've sort of I would say this paper I viewed as kind of like a snapshot in time. But you can imagine that there can be goals, sort of like the goals in explainable AI, to build tools to help us improve alignment. So I would say that there's sort of two broad ways to build these tools. One is to improve LLMs so they look more like us. One is to, make is sort of make not I wouldn't say improve us, but make how we interact with LLMs different. And so I can imagine there being, I think a fantastic tool would be something like, after you ask ChatGPT a question, if it could suggest another question for you to ask that would let you, more accurately figure out what it's good at and bad at. It's like, oh, you asked this question, and so you probably think I'm good at this, this, and this. However, to see what I really know, you should ask me this question. Like, I think a tool like that would be fantastic to develop. I'm not working on it now, but I can imagine. I hope some people are, and I can imagine working on it in the future. And I think that would be a really exciting sort of way. It's kind of in this field of human computer interaction, and the kind of intervention that I can imagine having a a large effect on understanding LLMs.
Yeah, thank you. So, anyone here on the audience, do you have more questions? Just feel free to raise your hand and come up the stage. And Eric and Kevin, please feel free to comment or ask questions if you have more. So, but I would like to say something also. It was just a thought that came to me the other day because, of course, I'm crossing a lot of yeah, comments or papers. I post about AI papers every day, but there was looking at the philosophical or looking at pattern recognition point of view. We had a small discussion with some of my friends about Ramanujan's parallelism of mathematical intuition and the way the modern AI models operate, because the Ramanujan, famously self-taught, absorbed mathematics through a collection of formulas, bypassing traditional methods of proof. So this method allowed him to develop an extraordinary intuition where he felt what the correct formula should be, often without initially providing formal justifications. And he would say that, whatever kind of proof I had thought of, or any formula, I saw it in a dream. So his reliance on patterns rather than on step-by-step proofs echoes the way AI models learn today through data patterns rather than explicit logic. In a sense, Ramanujan's approach is similar to how AI models like large language models function. And these models are trained on vast amounts of data and learn patterns and correlations, often arriving at impressive predictions without being taught the underlying rules or logic explicitly. So, just as Ramanujan could leap to complex conclusions that those conventional mathematicians took years to formalize, AI can produce highly effective outputs even if the internal mechanisms aren't fully transparent or interpretable in human terms. So, yeah, any comments about these two? And I don't know if this has some kind of parallel in maybe, if not now, in the future studies of your paper.
No, that's really interesting. I definitely had not made that connection. I will say that, comparing, I would say that just sort of, I think, would speak to the brilliance of Ramanujan, because he in some ways didn't have a head start. Like, he had far less data to train on than these large language models. He saw like a tenth of a tenth of a percent of a percent of a percent of a percent of all the text that they've seen. Yet he was able to perform, create mathematical discoveries that we just haven't gotten close to with large language models, and maybe never will. It's unclear.
Yeah, I also am reminded of John von Neumann, who's I forgot who was the professor who was afraid of him. He would try to teach a problem, an equation, and he said this is a problem that has been there for 100 years and it has not been solved. And at the end of the class, um, Van Neumann would give him a piece of paper and he had solved, that problem already. I think it was Stanislas Ulam. So maybe from some kinds of people, because this is human intelligence, there is a lot to learn. And through the large language models, there is also a lot to learn about human intelligence. But on the other hand, I just saw a talk by Eric Brynfolson that he said in 5 years' time, the human intelligence is going to become like narrow artificial intelligence. Yeah. So
I hope not.
I was curious why he said that. Actually, I just want to mention this.
You're curious why Brian Olson said that? Yeah, I don't know. I hope
Yeah,
not.
I'm very curious. I actually invited him because, of course, one of the motivations why I'm doing this room, because I have endless curiosity, and if there are new kinds of studies that are coming up, it leads to a lot of questions, even personally for me. So I invited him to come and tell us about it. But I'm not sure if he would be able to come. But I'm just very curious why he said that, and relate it to what the eminent scientists and computer scientists are saying about the future of AI. So yeah, I'm just thinking about it all the time in the past few days.
Mm. Yeah, I don't know him personally, but he's fantastic. He'd be a great person to have.
Yeah.
I
So go ahead.
sorry.
Who is this? Meleg? Meleg? Sorry if I
Hey,
mispronounced your name. Go ahead, please.
it's okay. You can call me Poodle. That's my usual name. Konnichiwa. なんだろう. Yeah, so I think he said that because, I mean, I can already see where large language models are in some ways more creative than humans. I mean, their depth of inquiry is very wide, wouldn't you say? They are rather creative. I mean, this is just my opinion. They are very creative. Um, I'm an artist. I make perfumes, so I don't really view creativity as coming up. I mean, my experience of creativity is nothing that, like, nobody comes up with completely new ideas. It's just taking bits of old information and then rearranging them into new ways. And, well, that's pretty much what culture is as well. But yeah, I view large language models as fairly, their depth of inquiry is very wide. Um, I don't know. It seems intuitive to me that and then the average individual human being has, well, basically hearsay, rumors, what they watch on the news, their own personal life experiences, whatever books they've read to draw from. Whereas large language models have the entire internet to draw. They cast a wider net. So I think, comparatively speaking, I can already see where we are more narrow than large language models in a way. I mean, if you're speaking purely from information, large language models don't have to think about locomotion or, I don't know, mating rituals.
Yeah, I think that's a great point, and I think that you brought up there something that was really interesting, which is that we large language models are creative, and they're creative in different ways than we are creative. And both us and large language models have limits to creativity. Here, humans, um, we're limited by like what you said. Like we just don't know that much stuff. We don't have access to all the texts. I mean, we maybe theoretically have access to a bunch of text, but we can't internalize them. Whereas large language models, they don't really have like coherent world models. They don't really understand what the world works. They're just pattern matching. And so I think like what's missing in a lot of the discourse is that we each have kinds of creativity that the other kind doesn't. And so finding ways to combine our creativities in ways that bring out that are sort of tailored to the best of our side are would be phenomenal. So I'm very curious. So you work in perfumes. Have you found LLMs to be helpful for your work?
Very helpful for my small business. Um, I kind of follow, I think it was only this year that I read Ray Dalio's Principles. And he said, begin with inquiry and with the assumption that you don't know everything you need to know. Right? So you're speaking to the difference between human intelligence and large language models. Well, one thing that we have to compete with or like contend with as human beings are our own prejudices. And I mean prejudice with like a capital P. Like we're very, very assumptive beings. We always
Absolutely.
assume one tragedy of the individual human being, or especially when it manifests in groups, um, is we don't know the limits of our own knowledge. Everybody on Clubhouse is it's very apparent if you go into the rooms, everybody's a fucking specialist in everything, right? So, but large language models, they don't really start from a point of ignorance. They draw from specialists' directly. Now, they're not perfect, but they do go to the specialists, right? Whereas your average human being will say, I saw that on the news, so it must be true, and I'm an expert in, that, whatever, the Israeli-Palestinian conflict because I saw it on the news, so I must know everything that's going on. So just starting from that point where large language models, although imperfect, do draw as a base starting point, like from specialists. I think and them not having real egos. I mean, that could be something that develops later on. Who knows? 10 years from now, they might get massive egos. But yeah, and then they don't have to contend with like biological. Um, oh yeah, please. They don't have to contend with like biological concerns like death or hunger or starvation or something like that. So I don't know. I just anyways.
Yeah, I will say like the one I mean there are many places in my life that I use large language models. The one that I found to be like by far the best is writing code. Like it has just absolutely changed the way I write code, and I am just so much better at writing code with large language models than I was before, to the point that I can't go back. I like haven't gotten like email sort of. I haven't gotten to LLMs in a good email workflow or other kinds of writing or menial tasks. But code, I just feel like they've completely knocked it out of the ballpark. It's been incredible.
Yeah, it's very much like Jarvis. It can help you enough so you can keep going with whatever crazy idea you have. At least that's how I found it to be as a helpful assistant. You still kind of have to know what to ask for, but you can also ask, like, what should I be looking for? And then, like, just even having that kind of expansion of the scope of the problem and the contraction of it back and forth, super helpful. I would say it's like on the level of a graduate student, and I'm not sure if folks here would agree, but it's almost that capable.
Yeah, it's very good at coding.
I think it's beyond the level of graduate, maybe a graduate sciences student, students in other fields. I don't know. Their worldview gets in the way sometimes, but purely scientific graduate student. Yeah.
I have a general question to make things to generalize. I was going to ask before, but uh, just just to make things more dreamy, maybe rather than 8 million questions, like I said, I would just say in your own words, since you're an expert, I'd like to hear like how do you think LLMs, limitations in contextual understanding, common sense, emotional intelligence, EQ, impact potential applications, I guess, maybe.
Yeah, I think it's a huge impact, or it'll have a huge impact, and I think that looking at the history of computer science, like there have been a couple of things that we really look for in all the things we develop. We want modularity, and we want like proofs of correctness. Like, and by the first one, I sort of mean like the mouse does what it does, the keyboard does what it does, and we can connect them and have them work the way they work. With LLMs, we lose that. Like we don't have like we sort of throw an Excel spreadsheet into an LLM and just like ask it to perform operations that we would normally think of as modular. So that's one. Two, the guarantee I think is the big one, that in all these modules of computing, we have guarantees. If you give a SQL command, you know exactly what it's doing. If you use an Excel spreadsheet and do an average, you know exactly what we're getting. And we need these guarantees aren't just nice, they're necessary to use and trust systems. And with LLMs, we're just not there. Like they don't have like they hallucinate, they don't have common sense. And like what we're finding is that there are some tasks that we're fine with without 100% guarantees. Like you don't need guarantees for everything. Coding is one of them. Like I don't need everything that LLM generates to be correct, because I have a decent enough BS filter when I code to know that to test whether what it did was right or wrong. And so for that, I'm fine. But there's other stuff where I can't possibly imagine using something unless I'm 100% sure what it'll do and what it won't do.
Yeah, thank you, Keyon. So we have Marco who came on stage. Marco, would you like to speak now? Maybe you have not opened your mic, so you are still muted. So please open your mic so that we can hear you if you are able to speak. If not, Bob can read. 2 minutes, please. So, yeah, he just made a comment on the room chat. So, while waiting for Marco, I want to ask this question from Ramon, who sent me a question here. He said, how could industries like healthcare, finance, or education benefit from understanding the alignment between human expectations and LLM performance? Could this research inform better decision making about where and how to deploy LLMs in critical tasks? And his second question is, do you foresee this research influencing the design of user interfaces or tools that help guide users in making better decisions about where to trust LLMs? Thank you.
Great. Yeah. So to answer the second question, the kind of tool I see is the one I described. Maybe 10 minutes ago, the one about sort of telling people which questions they should ask large language models to understand the capabilities of the large language model more or less. So I think that that sort of tool is exciting and something that I can imagine being developed. For your first question about what are the applications of this, I think absolutely. I think companies right now are trying to figure out how to use LLMs, like what they're good for and what they're bad for. And in some ways, the only way that they can figure out if an LLM is good at something is by running it for the thing. Like if you're McKinsey or some consulting company and you want to know if an LLM will be helpful in some kind of client meeting, like you kind of just have to run it in a client meeting or like do like a very extensive simulation to figure that out. So if an LLM is misaligned, like it'll be costly to run it for the things that you think it's good at and have it actually not be good at. And so there's sort of a nice paper called it's called like something about the jagged frontier, where it's a paper from Harvard Business School looking at how they're like working with McKinsey or some consulting company where they're trying to decide which tasks LLMs are used for in the company and which tasks that they aren't used for in the company. And they sort of find that like for some tasks the LLMs help humans a lot, and some tasks the LLMs like really don't help humans and sometimes maybe even hurt what humans would do without the LLM.
Have you found that there's issues where people's expectations of how to use these systems greatly affects their outcome? Like for example, like persona prompting is a great and like very useful technique for back and forth kind of brainstorming. But most people think it's kind of stupid, and they say that I'm playing Dungeons and Dragons, and I'm like, that's exactly what you have to do. Oh, and my cat is tripping here. Sorry.
Yeah, so like the way you and so this sort of like goes to the whole point that like you kind of need to specialize in interacting with LLMs to understand like how they can be helpful and how they won't be helpful. Like the instance of the first day LLMs came out, like none of us knew that this persona prompting would be useful. Like maybe we had hunches, but I'm sure we had hunches for other things that we thought would be useful that absolutely weren't useful. Um, so this sort of shows that like we and this is sort of saying like the generalization function depends, but like it changes between people. Like we all have different ideas about what the LM, about how to make the LM better and worse. We're getting better at knowing ways to make the LM behave more like we want it to. Although I think, or at least the evidence I've seen so far points to there just being a fundamental limit that we can get better and better and better, but there are always going to be cases like Alice, Bob, and Claire on the soccer teams where it'll get something completely right, change a small thing, get it completely wrong that we don't understand.
Yes, so we have Marco. Marco, are you able to speak now?
Oh yeah, yeah. Thanks for inviting me to the stage. Yeah, I think you guys have a lot of great points. Definitely learning a lot from what you guys are talking about. Um, I've had a lot of discussions with my brother. We both work in IT about LLMs and how they relate to like human intelligence and where it could go and where it is right now. Um, there's a lot of flaws in it. I don't think it's quite matching human intelligence right now or human capabilities. Even though it has access to the World Wide Web, I don't think that the ability to like there's a level of I guess understanding of like I guess, teams or the individuals that you're working with that LLMs just can't match right now. So basically, if you're not given these specific instructions or like a specific parameter, it's not gonna know that's that needs to be uncovered for that search result. Whereas a human may be able to fill in the blank. Given incomplete instructions, humans oftentimes can fill in the blanks and often pivot to make a better result than was expected initially. So I think that's where LLM falls short. But having access to the World Wide Web and depending upon the algorithm or the training, they do give very good results. But I just don't think they match the best human matchups at this point in time.
Yeah, yeah, I think that's right. There's sort of a nice paper out of Samuel, I forget the name of the paper, that sort of looks at the different like behavioral biases that LMs have and humans have. Like humans or like LMs, for example, like if you misspell a word like somewhat like incorrectly, like you just like change a letter, there are some ways that we can construct those such that humans can't perceive that like that letter that spelling change occurred, but you can always construct them in a way such that LLMs are just totally thrown off their game, which is hilarious. At the same time, there are things that like change how humans like that how humans respond to things. Like maybe we're risk averse. We have all these like biases that aren't reflected in LLMs, and so this is like an active area of research of trying to figure out which human bias like which what are the human biases, what are the LLM biases, and what are they good at, what are they bad at.
I have to. I mean, this is a really interesting thing. I don't know what kind of popped up in my head was like personality of LM user and how they go about using the the tool. Because I suppose you could call me like a creative, ADHD, hyperactive type person. I need to take my Ritalin. I see big pictures. I see the general goals ahead of me, but sometimes I need help filling in the details. And for me, LM is like it's so perfect for that, and it's almost intuitive to me. Like I never have. There's never. I'm never short of questions. Like I'm very very curious, very creative, but bad with the details. And I just find that large language models just really help me so much with my creative small business. For example, I have to send out a box of like three, I don't know, like 200 perfumes to Dubai this week or early next week, and like filling out the hazmat or the different types of paperwork. I just use ChatGPT for it, and it's pretty darn accurate. I do get a second person to check it over, but it helps me fill out those details so quickly. Um, I think if you have a general, if you know generally where you want to go, what your goal is, even if it's a little bit fuzzy in your mind, I think the LLMs can really help you carve a path towards that thing that you have in mind. So I have to say, Marco, I do kind of disagree, or maybe we're not disagreeing whatsoever. Maybe I'm misreading what you're having to say, but I think there's something about the personality or the way people press inquiry into the LLMs. I think I don't know. I don't know.
So I think you're at a really good point, which is that there are some places that LLMs are very, very helpful to us. And this is like a very broad characterization of those places. But how I would characterize what you're saying is they're good in places where it's hard for us to generate ideas, or it's hard for us to generate, but it's very easy for us to discriminate. So like given a generated thing, we can discriminate. So in your case, you're saying you have the LM generate the tag, the shipping label, and because and that would have taken you a lot of work, you still have someone who checks if it's correct. That's much less work than generating the tag itself. Same thing with me in code.
Much less. Yeah.
Same thing with me in code. Like writing code takes me a long time, but if someone gives me correct code, I can very easily say, I can run it a couple times and make sure it's correct or incorrect. So I would say those are sort of like two broad characteristics that are places where LMs are useful for us.
Yeah, I've gotten competitive when ChatGPT O1 preview says this took 5 seconds. I'm like, oh yeah, well this took me zero point 0.1 seconds to think of. So you my bitch still. So it's like a weird kind of like pettiness. But I feel like there's something to be said about how long the system thinks about it, and also in the way that we go about prompting it. Do you see like the habits of people changing over the course of the year? Like you said, people didn't know about persona hacking. Would you say there's something that's kind of up in the air right now that people really don't appreciate or don't understand that you think will become more commonplace with this respect?
Yeah, it's really hard for me to say because I feel like there's sort of two communities of LMs. There's like enthusiasts, like I imagine many of us, and there's sort of like lay people, like people who maybe used ChatGPT once when it came out, um, and haven't really used it since, like my mom probably. Um, I I can't speak for that community because I imagine that their things haven't shifted, and I I'm sure that our I know that like our the ideas we have are evolving and like we're getting better and better and better prompts. What I don't know is if we're plateauing or if we're or if we're still improving steadily. I would say like on the research side, it seems like the kind of excitement and the hacks is like is this thing I called like test time computation, like inference time computation, like having the model do more computation, like longer chains of thoughts or more like samples of chains of thought, or like getting an output and running some reinforced learning algorithm on an output, like taking longer and longer to generate, but getting like more accurate, but getting more accuracy as a result. Like that to me, I view I see at least on the research side as something that people are more interested in.
Oh, okay, cool, cool. Mr. Glass, I believe you're next, or Marco, if you had a follow up or something.
Uh, uh, at this point, Eric, I just want to ask because I know that there are many people who are interested to ask questions to Keyon. We've been here for 1 hour and 32 minutes. I just want to ask our speaker, how much more time does he have for us?
Yeah, I can go. Let's say 10 more minutes.
Okay, so we have on stage here Mr. Glass and Shan, and maybe Marco, if you have additional questions, if there's time, you can ask again after Mr. Glass and Shan have spoken. We will try to save, maximize the few minutes that our speaker be allowed to stay here because he is also very busy. So we have Mr. Glass on stage. Mr. Glass, are you able to speak now?
Excuse me. I, would- I would like to say, wonderful. Yeah.
Sorry, we didn't catch that.
I was saying that I enjoyed the conversation.
Thank you so much. I've had a great time here.
Yeah, and Shan? Are you able to speak too? Maybe you have you are and you don't realize it. Shan, if you're not able to speak, I'd like to ask Marco. I think he wanted to say something more a while ago.
Oh yeah, I just want to follow up with what was followed up from my earlier statements. I don't think that LLMs are a bad thing. I think that there are pros and cons for both LLMs and I guess uh, human thinking, I guess. But there's probably just a matter of time before it catches up to where there's going to be very marginal difference between the two, and in fact, I think it's going to easily surpass what humans are able to do. It's just a matter of updating that code and making it better, or maybe making that code maybe allowing that code to make itself better, like giving the right parameters for improvement. It'll incrementally grow itself in a matter of time. But yeah, that's all.
Yeah, I don't know. I guess I my view is that there are ways in which we've already surpassed human capabilities. There are ways that and we will probably never reach. I'm sure that there are ways that surpassed that we will absolutely never reach, and there are ways that we're better at them that I don't know if they'll ever reach. And it remains to be seen how much progress is made in each direction.
Yeah, why are we comparing? Why don't we just assume assume that we're different, you know, and the LLMs are them and we are us. And I think that the biggest thing with LLMs is that they can't really figure out feelings, although they're getting close. They are getting close. The big thing that LLMs seem to me to be missing is emotion, the ability to get down with emotion the way human beings can.
Dr. Francine, don't you think that the more these things advance, the more we're really going to question what it means to be human? You know, it's
Oh
like
yeah,
almost holding a mirror to our faces. And I find a lot of like, sort of like, what a lot of people are talking about is like, what does it mean to even be human?
yeah, for sure. That's a huge question. And and we haven't answered that. We never tried to answer that before artificial intelligence. We're not sure how the brain works yet, and not sure what consciousness consists of. So we've got a lot further to go. And hi, Eric, it's so good to see you.
Yeah, that's a I agree, and I think like I I think like a lot of the discourse now is about AI is replacing humans and automation. And Dr. Francine, you brought up a great point, which is what I'm most excited about, which is complementarity.
Yeah,
That
why don't we just work alongside each other? We have different strengths.
I can't
I
wait until my toaster starts arguing with like my pair of shoes and something about something that I'm wearing, and then I have to mitigate and let my lamp in as a mitigator and get adjudicator, and all of a sudden I have like this little mini series in my house of robots talking to each other. So every lamp will eventually be an LLM. We're doomed.
Yeah, I think the problem with that matter of thinking is it stifles innovation, right? So if we just digress and just say, hey, we're different from you and you're different from us, let's just be okay with that, we'll cease to innovate. But the
No,
more we
I
try
don't
to
think we
innovate
will.
and make it, well, I mean, if you're saying that we're good enough as we are, then why change? Good
Uh-uh.
enough is good enough, right?
No, it's not the same thing. That's not what I said. I said we have a lot to learn and we need to go on, but we don't necessarily have to duplicate large language models any more than they have to duplicate us. Unless all of life is prediction,
Well,
because
well, well, what you said was, why do we have to compare our intelligence to theirs, or
right,
vice versa? That's what you said.
yes,
But the
but
reason why you would compare it is to continue to make one better than it currently is. If it's not up to par of the latter, then you would continue to innovate to make it close to, if not better than the latter. But the
or
moment you say, hey, you're good the way you are, and I'm good the way I am, and we're just different, there's no need to innovate.
I don't know if I agree with that, but I don't have the energy to argue with you because if it were the
Yeah,
morning,
Yeah, no,
if it
yeah,
were
maybe
the
no,
we
it's no
will
morning,
make,
problem.
I'd
But
argue with you.
we will
yeah, I mean,
have
another room. But as far
another
as like the emotions, you'd have to really understand like, why do we have emotions? The reason why we have emotions is to move us towards a goal, right? To move us towards an objective. Machines don't really need that for the most part, right? They have code that tells them what their objective is, and there's nothing to delineate them from that objective. We have emotions that guide us towards something, right? Love guides you towards a mate. Anger,
Corey, we have
guys.
to close the room soon because our speaker does not have much time for us, and it was very difficult to invite this a very eloquent and a multidisciplinary speaker who was able to explain to us and present to us the beautiful slides. And we would like to thank him now for joining us. And yeah, I would like to give the mic to Keyon now. If you have some closing remarks or any comment before we close the event. And I would like to say that we really sincerely hope that we can invite you back here in Quantum Photonics. Thank you so much for the amazing talk. Keyon,
thank you
mic.
guys. Oh, sorry.
Ah, Yeah. Thank you so much. And Bob, do you have something to say before we try to close the room and give the mic to Darcel, and also Eric? I'd like to give you some chance to say something.
Spectacular discussion. Thank you very much, Doctor.
Yes. Um,
Thank you. I just want to say that I loved being here. I love the discussion afterwards. And I hope that you'll have me back because I would gladly do this again.
yeah, we will kidnap you, Keyon, to come back here in Quantum Photonics.
Great.
Yeah. Thank you so much. And now I'd like to give the mic to Darcel to do the countdown to close the room. Thank you, Darcel.
Thank you, Cecile, and thank you, Doctor, for a great talk. Excuse me. To close the room, we're going to start our countdown from lucky number 6. Is everybody ready?
Ready.
Me,
Ready?
Yay.
6.
Six.
6.
Thanks.
Six.
Sean 5.
5.
Mr. Glass 4.
Oh, sorry.
Four.
Mileg 3. Wow, this is going crazy.
Three.
What went wrong? Kevin? I don't know. 3.
Three.
Three. Three is a company.
Io Dos Equis.
Dos Equis, Cecile, Dos Equis.
More Dos Equis for Bob. Bob. Dos
Becky's
Equis.
the
More
three.
Dos Equis for Cecile.
Dos Equis.
Good, good doctor. You're number 1. Call out our last number, please.
1. Hi.
Woohoo.
Thank you so much, Keyon. Thank you, everyone. See you in our next rooms.
Bye bye.
Take care,
Bye.
buddy.